You are not moving, not slowly, not imperceptibly, not at all. Your speed relative to the chair you are sitting in is exactly zero, and that is not a trick of wording or some lesser kind of truth. It is a physical measurement, and every law of physics agrees with it. But here is what gets left out of the version you have heard. A speed is never a property a thing carries around with it. It is a relationship between two things, and the moment somebody names a different second object, the number changes completely. Against the ground beneath your feet, you are supersonic. Against the sun, you are doing nearly 30 kilometers every second. Against the center of this galaxy, 237. Every one of those is correct. Not one is truer than the others. And, this is the part almost every telling gets wrong, they cannot be added together. Which leaves one question worth asking. Is there anything in this universe to measure yourself against that you did not simply choose? Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will have the one number that answers that honestly, along with the 4 qualifications it arrives carrying. Now, let's slowly ease into this. Part 1. The correct answer is 0. Let us begin with the stillness, because it is real. Your velocity relative to the chair you are sitting in, or the bed you are lying on, or the floor beneath your feet, is 0. If you placed the most sensitive instrument humanity has ever built beside you and asked it a single question, "Are you moving?" it would return the answer 0, and it would be right. Not approximately right, not right in some limited local sense that a bigger truth will override in a moment. Right. We are going to spend the next 2 hours taking that answer apart, and by the end of it, you will have a number, a real one, measured to 5 significant figures, that describes how fast you are traveling through the universe. But I want to start here, at rest, because almost every version of this story you have ever heard begins by telling you that your sense of stillness is an illusion, and that is the one thing in this entire subject that is not true. Your stillness is not an illusion, it is a measurement. The trouble is not that the measurement is wrong. The trouble is that it is incomplete, and the missing piece is not a number at all. Here is the missing piece. In physics, a speed is never a property that an object carries around with it. It is a relationship between two objects. There is no such thing as the velocity of a thing. There is only the velocity of a thing with respect to another thing. Write down a speed and refuse to say what it is a speed relative to, and you have not written down a fact. You have written down half of a sentence and stopped. This sounds like a technicality. It sounds like the kind of correction a physics teacher makes to be irritating. It is neither. It is the deepest structural fact in this entire subject. It predates Einstein by nearly 3 centuries, and it is the reason the question in the title of this video is harder than it looks. Galileo wrote the clearest version of it in 1632, in a book that got him into a great deal of trouble for reasons unrelated to the passage I am about to describe. He asks you to imagine yourself below decks in the largest cabin of a ship, sealed in, with no windows. He gives you a bowl with some fish in it. He gives you a bottle suspended above a wide vessel, dripping steadily. He gives you some flies and some butterflies and a friend to throw a ball to. And then he asks you to watch, very carefully, everything that happens in that cabin, while the ship sits at anchor in a harbour. The fish swim in every direction with equal ease. The drops fall straight down into the vessel below. You throw the ball to your friend, and it takes the same effort whether you throw it toward the front of the ship or toward the back. The butterflies move about the cabin without any tendency to drift one way. Now, Galileo says, have the ship sail. Not accelerate, not turn, not pitch in heavy weather, but move steadily and smoothly across a calm sea at whatever speed you like. Watch again, and the answer is that nothing whatsoever changes. The fish still swim equally in all directions. The drops still fall straight down. The ball still takes the same effort in both directions. There is no experiment you can run inside that cabin, none, that will tell you the ship is moving. That passage is not a thought experiment about ships. It is a statement about the structure of reality, and it means something quite specific. It means that uniform motion is not a state an object is in, it is a relationship an object has, and a relationship requires two participants. So when somebody asks how fast you are moving, the honest response is a question in return, relative to what? Now, this is where the usual telling of this story goes wrong, and I want to flag it early because it is the trap the entire rest of this video is built to avoid. The usual telling says, but you are not really at rest because the Earth is spinning, so you are actually doing over 1,000 kilometers an hour. And then it says, but that is not the real answer either, because the Earth is going around the Sun, so you are actually doing 30 kilometers a second. And then the Sun around the galaxy, and the galaxy through the local group, each number bigger than the last, each one presented as though it were a more honest version of the one before, until you arrive somewhere in the hundreds of kilometers per second, feeling appropriately small. That story is enjoyable, and almost every part of it is factually correct. But its structure carries a claim that is false. It implies that these numbers form a ladder, with the small, honest but limited answers at the bottom, and the big true answer at the top. They do not. They are not rungs. Each one of those numbers answers a different question, because each one names a different second object, and I am going to show you before the halfway mark of this video that you cannot add them together, and that no one of them outranks another in any sense that physics recognizes. Which leaves us with something much more interesting than a ladder. It leaves us with a search. If every speed is a relationship, and every relationship requires you to choose a second object, then the whole question of how fast we are really moving collapses into one much sharper question. Is there any second object in this universe whose choice is not arbitrary? Is there anything to measure ourselves against that we did not simply pick? For about 200 years, physics had a candidate, and in 1887, two men in a basement in Ohio went looking for it, with the most sensitive optical instrument ever built, and found nothing at all. For about the last 60 years, physics has had a different candidate, and this one works. There is a number, and I will give it to you before we are finished, and it is quoted to a precision that no other velocity in your life comes close to. But it arrives carrying 4 qualifications, and every one of them is stranger than the number itself. Newton incidentally hated this conclusion. In the scholium that opens the Principia in 1687, he insists that there is such a thing as absolute space, existing in its own nature, without relation to anything external, always similar and immovable, and that true motion is motion with respect to it. He was clear-eyed enough to admit in the same passage that he had no way of detecting it. Leibniz went after him for exactly that admission. If absolute space is real, Leibniz argued, then the decision to place the entire universe 10 meters to the left of where it is would be a real decision, with a real answer that nothing anywhere could ever reveal. A difference that no possible observation could detect, he said, is not a difference. That argument was published in 1716, and it has never really been answered. There is one more thing worth noticing before we move, and it will matter more than it seems to. Put an accelerometer on your desk. It is a small device, it costs almost nothing, and there is one in the phone in your pocket. Ask it about every single speed I am going to quote you over the next 2 hours. It cannot detect any of them, not one. It reads one Earth gravity, pointing upward, and nothing at all sideways. And it will keep reading that whether the answer to our question turns out to be 0 or 1,000,000 kilometers an hour. Every instrument that has ever successfully measured our motion has done it by looking at something outside. Before we can get anywhere near it, we have to climb the ladder that is not a ladder. So let us start with the number you have almost certainly heard before, the one about the spinning Earth, and let us find out exactly where it goes to zero. Part 2. The number everyone recites. The Earth turns once on its axis every 23 hours, 56 minutes, and 4 seconds. Not 24 hours. 24 hours is how long it takes the sun to return to the same place in your sky, and that is a slightly different question, because in the course of one rotation, the planet has also moved a little way along its orbit and has to turn a few extra minutes worth to catch the sun up. The true rotation, measured against the distant stars, takes 23 hours and 56 minutes. The circumference of the Earth at the equator is 40,075 kilometers. Divide one by the other, and you get the number that appears in every version of this story ever told. About 1,674 kilometers per hour. 465 meters every second. Sit with that for a moment, because the comparison is genuinely worth making. The speed of sound at sea level in ordinary air is about 340 meters per second. If you are somewhere near the equator, the ground you are standing on is moving at roughly 1 1/3 times the speed of sound. A commercial airliner at cruise does around 250 meters per second. The ground is comfortably faster. And you feel none of it, which is the first thing everybody wants explained. The explanation is not that the effect is too small to notice. The explanation is that there is no effect to notice, because bodies do not respond to velocity at all. Bodies respond to changes in velocity. That is what an accelerometer measures. That is what your inner ear measures. And that is what the pressure of a seat against your back measures. Steady motion produces nothing. This is Galileo's cabin again, wearing different clothes. There is one small piece of the rotation that does produce a real, measurable effect, and it is worth stating precisely because people who deny that the Earth turns tend to raise it as though it were unanswerable. Going in a circle is not uniform motion. It requires a continuous change in direction, which is an acceleration, and that acceleration is measurable. At the equator, it comes to about 0.034 meters per second squared, which is roughly 1/300th of gravity. That is far too small for your body to register as a sensation, but it is not too small for an instrument. Gravity at the equator is measurably weaker than gravity at the poles, by about 0.5%. Part of that difference comes from the rotation itself, and part of it comes from the fact that the planet has been pushed into a bulge by the rotation, so the equator is about 21 kilometers further from the center of the Earth than the poles are. A precision balance registers it. Rocket engineers exploit it, which is why launch sites cluster as close to the equator as national geography allows. So the rotation is real, and it is detectable from inside a sealed room. But the number itself has a property that nobody ever mentions, and it is the first crack in the whole enterprise. The number depends entirely on where you are standing. 1,674 kilometers per hour is the equatorial figure. At 45 degrees latitude, roughly the latitude of Milan, or Montreal, or Christchurch, the circle you are being carried around is smaller, and the speed drops to about 328 meters per second. Move further north or south, and it keeps falling, and if you go all the way and stand precisely at the geographic South Pole, the number becomes 0. You are not carried anywhere. You simply pivot, once a day, on the spot. Now hold 2 people in your head at once. One is standing at the pole. One is standing in Quito, Ecuador, almost exactly on the equator. According to the number everybody recites, one of them is motionless and the other is supersonic. And there is nothing whatsoever different about the 2 people. Same bodies, same physics, same planet, same instant. What changed was not either person. What changed was the geometry of the relationship between them and the second object the question quietly assumed, which was the Earth's rotation axis. That is the pattern, and I want you to hold on to it, because it repeats at every level of this video, and it is the thing the ladder-shaped version of the story hides. A speed that changes when you walk somewhere without accelerating is not a property of you. The history of how we came to know this number is worth a moment, because it took an extremely long time, and it happened in the wrong order. Eratosthenes of Cyrene, working as chief librarian at Alexandria around 240 years before the Common Era, measured the size of the Earth. The method was almost embarrassingly simple. He had a report that on the summer solstice, at noon, in the town of Syene to the south, the sun stood directly overhead and a vertical stick cast no shadow at all, and sunlight reached the bottom of a well. At Alexandria, on the same day at the same hour, a vertical stick did cast a shadow, and the angle worked out to about 1/50th of a full circle. If the sun's rays arrive effectively parallel, then Alexandria and Syene must be 1/50th of the way around the planet from each other. Multiply the distance between them by 50 and you have the circumference of the Earth. Depending on which version of the stadion he was using, he landed somewhere within a few % of the modern value. But Eratosthenes was not measuring a speed. Nobody was measuring a speed, because nobody thought the ground was going anywhere. The demonstration that the ground turns beneath us, made without any reference to the sky at all, did not arrive until February of 1851, when Leon Fouquet hung a 28-kilogram brass sphere on a 67-meter wire from the dome of the Pantheon in Paris. A pendulum, once set swinging, keeps swinging in the same plane because there is nothing to push it sideways. Foucault set his going and asked the crowd to watch the plane of the swing. Over the course of an hour, it turned about 11 degrees. Over the course of about 31.5 hours, at the latitude of Paris, it came all the way around. The pendulum was not turning. The building was. And the reason this experiment is the correct place to end this part is that it is the only measurement in this entire video that needed no second object at all. Foucault detected the Earth's rotation from inside a closed room, with the doors shut, because rotation is an acceleration, and accelerations are absolute in a way, velocities are not. Foucault's pendulum is not the only positive detection from inside a closed room, either, and the others are worth knowing because they close the argument completely. Drop an object down a deep mine shaft, and it does not land directly below where you released it. It lands very slightly to the east, because at the top of the shaft it was further from the axis, and therefore moving eastward a little faster than the floor at the bottom. Fire an artillery shell far enough, and it curves, consistently, to the right in the northern hemisphere and to the left in the southern, which is why long-range gunnery tables have a correction column for it, and why weather systems spiral the way they do. None of these requires a window, a star, or an appeal to authority. They are the rotation, showing up as a force in a sealed box, which leaves us in an awkward position. We have a number, we know where it came from, and we know it goes to 0 if you walk far enough south. So let us change the second object, step off the planet entirely, and look at the number that most people would say is the real one. Part 3. The man who proved it by accident. The Earth's average speed around the Sun is 29.78 kilometers per second. That is about 107,000 kilometers per hour. It is roughly 64 times faster than the equatorial rotation we just left behind, and it is the number that most people, if pressed, would name as the honest answer to how fast we are moving. Over the course of a year, the planet covers about 940 million kilometers, and it does not cover it evenly, because the orbit is not a circle. Its eccentricity is 0.0167, small but not nothing, which means that in early January, at the closest approach, we are doing 30.29 kilometers per second, and in early July, at the furthest, we are down to 29.29. The difference across the year is about 3.4%. You are measurably faster in winter, if you happen to live in the northern hemisphere, and there is no way for you to tell. Here is what I find remarkable about this number. Humanity argued about whether it existed at all for roughly 2,000 years, on grounds that were entirely aesthetic and mathematical, and when the physical proof finally arrived, it arrived by accident, and it came from starlight arriving very slightly off target. Aristarchus of Samos proposed a sun-centered arrangement around 270 years before the Common Era, and was largely ignored. Copernicus revived it in 1543, and the argument in its favor was that it made the mathematics of the planets far cleaner. Kepler, from 1609, made it cleaner still by allowing the orbits to be ellipses. Galileo argued for it publicly and was made to stop. But not one of those was a measurement of the Earth's motion. They were arguments that the model worked better. A committed opponent could always answer, correctly, that a model working better is not the same as a model being true. What everybody agreed would settle it was stellar parallax. If the Earth really swings across a diameter of about 300 million kilometers over 6 months, then a nearby star, viewed from opposite ends of that swing, should appear to shift slightly against the more distant background. Find the shift, and the argument is over. Fail to find it, and either the Earth is stationary or the stars are unimaginably far away, and for most of that period, the second option seemed absurd. So in the 1720s, James Bradley and Samuel Molyneux set out to find it. Imagine the instrument. It is not a telescope you point. It is a zenith sector, a long tube fixed almost vertically and braced against the structure of the house itself, at Molyneux's home at Kew, so rigidly that it cannot be nudged. It looks at one strip of sky only, the strip directly overhead, because a star seen straight up is looking through the least amount of atmosphere, and its position is least corrupted by refraction. The observer does not stand. He lies on his back beneath the eyepiece in the dark, in December, and waits for one particular star to drift across the field. The star is Gamma Draconis, in the head of the dragon, and from London it passes almost exactly through the zenith. Night after night, from December of 1725, they take its position and write it down, and the star moves. It genuinely moves, and the movement is far too large and far too regular to be an error. For a few weeks, it looks like the discovery of the century, and then they keep watching, and the pattern refuses to behave. Parallax should reach its extremes when the Earth is at the two ends of its orbital swing. The shift they are seeing reaches its extremes 3 months out of step with that, at the points where the Earth is not furthest to one side, but moving fastest to one side. The displacement does not depend on where the Earth is. It depends on which way the Earth is going. That is the wrong answer, and it is the wrong answer in a very specific and informative way, and it took Bradley about 2 years to see what it meant. The story that has come down to us is that the answer arrived on a boat on the Thames. He noticed the wind vane at the masthead changing direction each time the boat changed tack, even though the wind itself had not changed at all. The apparent direction of the wind was a combination of the real wind and the boat's own motion. Whether or not the anecdote is literally true, it is exactly the right physical picture. Light arrives at a finite speed. If you are moving sideways while it comes down the tube, you have to tilt the tube very slightly forward to catch it, in precisely the way you tilt an umbrella forward when you run through vertical rain. The apparent position of every star in the sky is displaced slightly toward the direction the Earth is traveling. The size of the displacement is set by one ratio, and only one, the Earth's speed divided by the speed of light. Bradley measured that displacement as about 20.5 arcseconds. He announced it in a letter to Edmond Halley, published in the Philosophical Transactions in 1729, and with that letter, 3 things happened at once. The first is that the Earth's motion around the Sun stopped being an argument and became an observation, not a model that fits better, a thing seen. The second is that Bradley had accidentally weighed the speed of light. He knew the Earth's orbital speed reasonably well from the geometry of the solar system, and he now had the ratio, so he could divide. He got something around 301,000 kilometers per second, which is within 1% of the modern value, and it was the best figure available for most of the following century. The third is the part I like best. Bradley had failed. He had been looking for parallax for 2 years, and he did not find it, because it was too small. Stellar parallax was not detected by anyone until Friedrich Bessel measured it for 61 Cygni in 1838, 110 years later. The largest parallax in the entire sky, that of Proxima Centauri, is 0.77 arcseconds. Bradley's aberration is about 27 times bigger. He was hunting a small effect and stumbled over a much larger one nobody had predicted, sitting directly in front of him the whole time. The shape the effect traces is worth picturing, because it makes the geometry concrete. Over the course of a year, every star in the sky draws a small ellipse. For a star sitting directly at the pole of the Earth's orbital plane, the ellipse is a near-perfect circle, about 41 arcseconds across. For a star lying flat in that plane, the ellipse collapses into a straight-line segment, back and forth, of the same length. Everything in between traces an ellipse of some intermediate flattening. The entire sky is doing this, all the time, and it has been doing it since long before anyone thought to look. 41 arcseconds is a small angle. The full moon is about 1800 arcseconds across, so the whole of the heavens is swinging back and forth each year through a path roughly 1/40th the width of the moon, and that swing is the direct fingerprint of a planet moving at 30 kilometers a second. It is still there. Aberration has not gone away, and it is not a historical curiosity. Every modern astrometric catalogue has to correct for it, and the Gaia spacecraft, which measures positions for well over 1 billion stars, does it as routine bookkeeping. Gaia has even gone one better. In its data release in 2020, the team reported that they had detected the change in aberration caused by the solar system's acceleration as it curves around the galaxy, showing up as a systematic drift pattern of about 5 microarcseconds per year, spread across more than 1 million distant quasars, from which they extracted an acceleration of roughly 2.3 nanometers per second squared. That is not a speed, that is a measurement of the fact that our speed is turning. So we now have 2 numbers, and they came from 2 completely different second objects, and I want to note before we move on that you cannot combine them into anything. But we are not ready to make that argument yet, because there is one more thing to do first, and it is the most important experiment in this entire video. For 200 years, physics had one candidate for a true state of rest. In 1887, 2 men went looking for it. Part 4. The experiment that went hunting for really. Through the whole of the 19th century, physics had an answer to the question this video is asking, and it was a good answer, arrived at by careful reasoning, and it was wrong. The reasoning went like this: light is a wave. That had been established beyond serious dispute by Thomas Young's interference experiments at the start of the century, and then sealed by James Clerk Maxwell in the 1860s, when he showed that the equations of electricity and magnetism, taken together, predict a wave that travels at a speed you can calculate from 2 laboratory constants, and that speed turned out to be the speed of light. Light was an electromagnetic wave. That was settled. But every wave anyone had ever met was a wave in something. Sound is a wave in air. Ripples are waves in water. A wave is not a thing that travels. It is a pattern of disturbance that travels through a thing. So if light is a wave, there must be a medium filling all of space that light is a wave in. They called it the luminiferous ether. And here is why the ether matters for us. If it exists, then it is the one thing in the universe that could sensibly be described as being at rest. Not because it is special in some mystical sense, but because it is everywhere, and it is what light is a disturbance in, so the speed of light would be measured relative to it. That makes the ether the second object we have been looking for since the start of this video. It would give the word really an actual referent. There would be a true answer to how fast you are moving, and it would be your speed with respect to the ether. Better still, it would be measurable. The Earth is going around the Sun at 30 kilometers a second. Unless we happen to be permanently at rest with respect to the ether, which would be an extraordinary coincidence, we must be moving through it, and there must be an ether wind blowing past this planet. And a wind changes how fast waves reach you, depending on whether you are looking upwind, downwind, or across. Albert Michelson had built the instrument to detect it. He was, by common consent, the finest optical experimentalist alive, and he had already tried a version of the measurement alone in Potsdam in 1881 and got an ambiguous result that he was not satisfied with. So in 1887, working with the chemist Edward Morley in Cleveland, Ohio, he built it properly. Picture the apparatus, because the physical details matter. A slab of sandstone, about 1.5 meters square and roughly 1 foot thick, sits in the basement of a dormitory building. The slab is not on a table. It is floating in a circular trough of liquid mercury, so that the whole thing can be turned smoothly through any angle without the stone flexing by even a fraction of the width of a light wave. On top of the stone are mirrors. A beam of light comes in, meets a half-silvered surface, and splits in two. One half travels out along one arm, the other half along an arm at right angles. Mirrors at the far ends bounce each beam back and forth several times, so that although the stone is only 1.5 meters across, each beam actually travels about 11 meters. Then the two halves are brought back together and allowed to interfere, producing a pattern of light and dark bands in an eyepiece. If there is an ether wind, then one arm is lying more nearly along it and the other more nearly across it, and light takes very slightly different times to complete the two round trips. Rotate the whole slab and you swap which arm is which, and the interference bands should slide sideways. Michelson and Morley calculated the expected slide at about 4/10 of a band. Their apparatus could see a slide of about 1/100th of a band. They had a margin of 40-1. They took their readings at night, because footsteps elsewhere in the building were enough to disturb the fringes. They walked slowly alongside the floating stone as it turned, reading the eyepiece, marking the numbers. They did it in July, and then again at other points in the year, so that the Earth's own orbital direction would have changed, in case they had been unlucky enough to catch a moment when the Earth's motion happened to cancel the Sun's motion through the ether. And they saw nothing. Not a small effect, not a marginal detection. Their upper limit on the Earth's speed through the ether came out below about 8 kilometers per second, and later refinements pushed it below 5, against an expectation of 30. Whatever they were looking for was not there. I want to slow down here, because this is one of the two moments in this video where the physics stops being an argument and becomes a person. Michelson did not experience this as a triumph. He experienced it as a failure, and he never really stopped experiencing it that way. He had built the most sensitive optical instrument on the planet to detect the medium that light traveled through, and it had detected nothing, and to him that meant the experiment had not worked. He went on running variations of it. He was still running them in the 1920s, decades after the theoretical world had moved on. He received the Nobel Prize in Physics in 1907, the first American ever to win one in any science, and the citation was for his optical instruments and the measurements he made with them. He died in 1931, at the age of 78, and by most accounts he was never fully at peace with what his own result had done to physics, which is the sad and beautiful thing about it, because he had not failed at all. He had succeeded at something much larger than the thing he set out to do. He did not fail to measure the ether wind. He measured the fact that there is no ether wind, and therefore no ether, and therefore no absolute rest. The result is not an absence of data. It is data. It is one of the most consequential single measurements in the history of the subject, and the man who made it spent 40 years being right about the wrong thing. The rescue attempts came first. George Fitzgerald and Hendrik Lorentz independently proposed that objects moving through the ether contract along the direction of motion by exactly the amount needed to shorten the arm and cancel the effect. That is not as absurd as it sounds, and it produces the correct mathematics. But it has an unmistakable smell to it, because the contraction has to be precisely the amount required to hide the ether at every speed, in every direction, in every experiment. A medium that arranges for itself to be permanently undetectable is not doing much work. It is worth saying plainly that the ether was not a fringe idea held by cranks. Maxwell believed in it. Lord Kelvin believed in it. Lorentz built a substantial and successful body of physics on top of it. Maxwell's own last published thoughts on the problem, in a letter written in 1879, suggested using the timing of Jupiter's moons to look for the effect, and it was that suggestion, published after his death, that set the young Michelson off in the first place. The ether was the consensus, and the consensus was reasonable, and it was destroyed by a measurement. The experiment has been repeated hundreds of times since, with better and better instruments, and the story of one of those repetitions is worth a sentence. In the 1920s, Dayton Miller, who had worked with Morley, reported a small but persistent positive signal from a mountaintop apparatus, and for a while it was taken seriously enough to worry people. It was eventually traced to temperature gradients across his equipment. It is a clean example of a systematic error surviving longer than it should have, because it was giving somebody the answer they wanted. The modern versions of the experiment use cryogenic sapphire resonators and have pushed the limit on any directional dependence of the speed of light below 1 part in a million. Einstein's paper of 1905 took the other road, which was to stop trying to hide it. If no experiment can detect the ether, do not build a theory in which it exists and conceals itself. Build a theory in which it does not exist. The speed of light is the same for everyone. Uniform motion has no absolute meaning, and the null result is not a puzzle to be explained away, but the plain content of how the world is. That is where we stand. 2 centuries of physics had one candidate for a frame that deserved the word really, and it was hunted down and found not to exist, and the hunt is now regarded as one of the great successes of experimental science. So we are back where part 1 left us, with a growing pile of numbers, and no principled way to choose among them. Let us add the biggest one yet, and look at how we know it, because the chain that produced it is one of the cleanest measurements in modern astronomy. Part 5. 230 kilometers per second. The Sun is in orbit around the center of the Milky Way at something close to 230 kilometers per second, and I want to tell you how that number is actually obtained, because it is not a guess, and it is not an estimate from a model. It comes from 2 measurements multiplied together, and almost nothing else. The first measurement is an angle. At the center of our galaxy there is a compact radio source called Sagittarius A star. We now know it to be a black hole of about 4.3 million solar masses, and it was photographed, after a fashion, by the Event Horizon Telescope. But long before that, radio astronomers had been tracking its position on the sky with extraordinary precision, using the Very Long Baseline Array, a set of 10 radio dishes strung from Hawaii to the Virgin Islands that work together as a single instrument the width of the Earth. Over years of observation, Sagittarius A star was seen to drift across the sky. Mark Reed and Andreas Brunthaler measured that drift at 6.379 milliarcseconds per year, with an uncertainty of about 26 microarcseconds, essentially all of it along the plane of the galaxy. To give you a sense of what a milliarcsecond is, it is the angle subtended by a coin about the size of your thumbnail, placed 4,000 kilometers away. Now here is the beautiful part. That drift is almost entirely not the black hole's motion. It is ours. 4 million solar masses sitting at the bottom of the galaxy's gravitational well does not go anywhere in a hurry, and the same observations that measured the drift also confirmed this directly, by showing that its motion perpendicular to the galactic plane, where our own orbit contributes almost nothing, is under about 1 kilometer per second. So the great sweep across the sky is the reflection of the Sun's own orbital motion, projected onto a fixed point. But an angular rate is not a speed. To convert one into the other, you need a distance, and the distance to the center of the galaxy has been one of the hardest numbers in astronomy for most of a century, because it sits behind an enormous amount of dust. The second measurement solved it, and it did so by watching a single star go round. In the crowded region right at the galactic center, there is a star designated S2. It is a young, hot, bright star, and it is on a highly elongated orbit that takes it around Sagittarius A star once every 16 years. 16 years is a long time to wait, but it is a human length of time, and astronomers have now watched it complete more than one full circuit. In 2019, the Gravity Collaboration reported a result using a technique that combines the light from all four 8.2-meter telescopes of the Very Large Telescope in Chile into a single interferometer, giving an effective resolution far beyond any one of them. By tracking S2 through its orbit, including the moment of closest approach when it whips past the black hole at nearly 3% of the speed of light, they extracted a purely geometric distance to the galactic center, 8,178 parsecs. The uncertainty was 13 parsecs statistical and 22 systematic. That is a precision of about 0.3% on a distance of roughly 26,700 light-years, obtained by watching one star complete one orbit. Multiply the angular drift by the distance, and you get the Sun's total velocity across the sky, as seen from the galactic center. It comes out around 247 kilometers per second, of which the circular part, the bit that is genuinely orbital motion, rather than the Sun's own local wandering, is somewhere near 237. That is the number. An angle measured over 2 decades of radio observations, multiplied by a distance measured by watching one star. Remove either one, and the number ceases to exist. Take a moment with what it means. At 237 kilometers per second, you would cross the Atlantic, London to New York, in about 23.5 seconds. You would cover the distance from the Earth to the Moon in roughly 27 minutes, and it is still only about 0.08% of the speed of light, which tells you something quite bracing about how much room there is above this number. One full circuit of the galaxy at that speed takes somewhere between 220 and 250 million years. Astronomers sometimes call it a galactic year. The Sun has been burning for about 4.5 billion years, which means it has completed something on the order of 20 of them, and no more. 20 laps in the entire life of the solar system. Before we leave the number, I want to be honest about its flaw, because this video is going to end on a point about precision, and it would be dishonest to be sloppy here. The Gravity Collaboration refined its own result 2 years later and got 8,275 parsecs, with a quoted precision of about 0.4%. Compare that with the earlier 8,178, and you will notice something. The two values differ by about 1.2%, which is 3 or 4 times larger than either of their stated uncertainties. Neither team did anything wrong. This is simply what a real measurement chain looks like when you push it. The error bars quoted are the ones the analysis can account for, and there is always a little more slop in the world than any analysis accounts for. Hold on to that, because in about an hour we are going to meet a velocity quoted to 5 significant figures, and I am going to ask you the same question about it. there is a second thing hiding in these observations that is worth pulling out. The fact that Sagittarius A star barely moves at all, under a kilometre per second, perpendicular to the plane, is one of the strongest arguments that it really is an enormously massive object, anchored at the dynamical centre of the galaxy, rather than some bright but ordinary source that happens to sit near the middle. Light things get pushed around by everything near them. Heavy things do not. Its stillness is its mass, showing itself indirectly, in a measurement that was never designed to reveal it. Which produces one of the genuinely useful pieces of perspective in this subject. 1 galactic year ago, the very first dinosaurs had not yet appeared. Life on this planet was recovering from the largest extinction event in its history. The last time the Sun was at this point in its orbit, essentially every organism you have ever seen a picture of did not exist yet. Except that it was not at this point in its orbit, because the orbit does not close. The Milky Way's rotation is not Keplerian, which is to say the outer parts do not slow down the way objects orbiting a concentrated central mass are supposed to. The rotation curve stays roughly flat all the way out, which is the observation that made dark matter unavoidable in the first place. A consequence of that flatness is that the Sun's orbit precesses. It has never returned to the same physical spot in the galaxy, and it never will. The path is a slowly drifting rosette, not a circle. And there is one more layer folded into that motion. One that the latter version of this story almost always skips, because it is small and awkward, and does not sound impressive. The Sun is not simply going round, it is also bobbing. Part 6. The layer nobody recites. The Sun is moving relative to the stars around it at about 18 kilometers per second. That layer almost never appears in the standard tour, and I think it is because it is small. 18 kilometers per second sounds unimpressive next to 230, but it is one of the most physically real numbers in this video, because unlike the galactic orbit, which is measured against a point 26,000 light-years away that we can only see in radio waves, this one is measured against the neighbors. It is the Sun's motion relative to the average of the stars in its own vicinity, a reference that astronomers call the local standard of rest. The best-known modern breakdown of it splits the motion into 3 components, about 11.1 kilometers per second inward, toward the galactic center, about 12.24 in the direction of galactic rotation, which is to say we are overtaking the local average slightly, and about 7.25 straight up, out of the plane of the galaxy. That third number is the one that changes the picture, because it means the Sun is not traveling in a flat circle. It is going up and down. The disk of the galaxy has mass in it, and that mass pulls the Sun back toward the midplane whenever it strays, so the Sun oscillates, rising above the plane, slowing, falling back, passing through, rising below. The full cycle takes somewhere on the order of 60 million years, with a midplane crossing roughly every 30. At the extremes, the Sun gets perhaps 100 parsecs from the midplane, which is a few hundred light-years. Right now, we are about 20 parsecs above it, roughly 65 light-years up, and rising. Put those together, and the actual path of the Sun through the galaxy is not a circle and not even a rosette. It is a slowly drifting rosette with a gentle vertical wave running along it, like a horse on a carousel that is also on a very slightly wobbling floor. And the Earth is corkscrewing around that once a year at 30 kilometers a second, while spinning once a day. This is the point at which I have to address a video that a great many people have seen. There is a widely shared animation, in various versions, that shows the solar system not as flat rings, but as a corkscrew, with the Sun charging forward and the planets trailing behind it in helical paths, and it is usually presented with a caption suggesting that the model you were taught is a lie, and this is the suppressed truth. The underlying observation is entirely correct and entirely unremarkable. In a frame that moves with the galaxy, rather than with the Sun, the planets do trace helices. Of course they do. A point on the tire of a moving car traces a cycloid relative to the road, while tracing a perfect circle relative to the car. Neither path is the deception, and neither is the truth. They are the same motion, described against two different second objects. That is this entire video in one sentence, and the animation is accidentally an excellent illustration of it. What the animation gets wrong is the geometry, and the errors are specific. It shows the plane of the planets standing perpendicular to the Sun's direction of travel, so the planets appear to be dragged along behind, like the tail of a comet. In reality, the ecliptic, the plane the planets orbit in, is tilted about 60 degrees to the plane of the galaxy, and the Sun's velocity vector lies much closer to the ecliptic plane than perpendicular to it. The true figure is a wide, shallow, gently leaning helix, not a tight vortex. The animation also implies that the Sun leads and the planets lag, as though they were being towed. Nothing is towing them, they are in orbit, and the entire arrangement is moving together, which is exactly what Galileo's cabin says has to happen. So the version of the sky in that animation is wrong in its details and right in its lesson, which is that the shape of a path is not a fact about the object. It is a fact about the pair. Now, the local standard of rest gives the Sun a direction as well as a speed. Add those three components together, and the Sun is heading toward a point on the sky called the solar apex, which sits in the constellation Hercules, close to the border with Lyra. If you are in the northern hemisphere on a summer evening and you find Vega, the brightest star in that part of the sky, you are looking within a few tens of degrees of the direction the Sun is actually going with respect to its neighbors. There is nothing to see, but that is where we are headed. And we are headed into something, which is the part I find genuinely strange. The Sun is not traveling through empty space. It is inside a cloud. The local interstellar cloud is a wisp of warm, partly ionized gas, roughly 30 light-years across, with a density somewhere near 0.3 atoms per cubic centimeter. That is emptier than the best vacuum any laboratory on Earth has ever produced, by a very wide margin. And it is still a cloud, and we are inside it, and we are moving through it at about 26 kilometers per second. The cloud, in turn, sits inside a much larger and much emptier cavity called the local bubble, about 300 light-years across, which appears to have been carved out by a series of supernovae several million years ago. So the arrangement is a bubble inside the galaxy, a cloud inside the bubble, the heliosphere inside the cloud, and the planets inside that. We have measured the wind. 2 spacecraft have gone far enough out to leave the Sun's own bubble of solar wind and taste the interstellar material directly. Voyager 1 crossed the heliopause on the 25th of August, 2012, at a distance of 121.5 astronomical units. Voyager 2 followed on the 5th of November 2018 at about 119. They are the only human-built objects that have ever done it. They are both still transmitting, and they are the only direct measurements we have of what the Sun is actually moving through. It is worth pausing on how thin that cloud is, because the word cloud does a lot of misleading work. 0.3 atoms per cubic centimeter means that in a volume the size of a sugar cube, there is, on average, about 1 atom every 3 cubes. The best hard vacuum ever achieved in a laboratory on this planet is still several thousand times denser than that. If you scooped up a cubic kilometer of the local interstellar cloud and condensed it, you would have a wisp of gas you could barely detect. And yet across the distances involved, that wisp is enough to define a boundary, to hold off the Sun's outward wind at a measurable radius, and to be pushed into a shape by our passage through it. There is also a genuine open question wrapped up in this layer, which is what happens when the Sun leaves. We entered the local interstellar cloud somewhere between 2,000 and 100,000 years ago, and we will pass out of it in something like 10 to 20,000 years. Denser or thinner surroundings change the size of the heliosphere, and the heliosphere is what deflects a substantial fraction of the galactic cosmic rays that would otherwise reach the inner planets. Whether that has ever mattered for the history of this planet is not established, and claims that it has should be treated carefully. But the fact that our local environment changes at all, on timescales shorter than the history of agriculture, is a reminder that even the quiet layers of this ladder are not static. So that is 5 numbers now. 0 against the chair, 465 meters per second against the rotation axis, unless you are standing at the pole, in which case 0 again. 29.78 kilometers per second against the sun, 18 against the local stars, 237 against the center of the galaxy. It is time to stop climbing and look at what we have got, because the pile has a problem in it that nobody ever mentions. Part 7. The ladder is not a ladder. Let us step back and put the pieces together, because we are about halfway through and the pile is now big enough to see the shape of. We have 5 numbers: 0, 465 meters per second, 29.78 kilometers per second, 18 kilometers per second, and 237 kilometers per second. Every one of them is correct. Every one has been measured, several of them to remarkable precision, by different people using different instruments across 3 centuries. And now comes the moment where the usual telling of this story does the thing I have been promising to refuse. It adds them up. You have probably seen the total. It comes out somewhere in the vicinity of 280 kilometers per second, and it is presented as the grand answer, the true speed, the number that finally accounts for everything. It is nonsense, not approximately right, not right in spirit. It is a category error, and once you see why, you cannot unsee it. Here is the reason. Each of those 5 numbers names a different second object. 465 meters per second is your speed relative to the Earth's rotation axis. 29.78 kilometers per second is the Earth's speed relative to the Sun. 18 is the Sun's speed relative to the average of the nearby stars. 237 is the Sun's speed relative to the center of the galaxy. These are 5 different relationships involving 7 different objects, and adding them is like adding your height in centimeters to your age in years and your postcode. The arithmetic will complete. The result means nothing. There is a narrower version of the objection that is also true and worth having, which is that even where the objects do chain properly, velocities are vectors. They have directions. Your rotation speed points east. The Earth's orbital speed points along the tangent of the orbit, in a direction that reverses over 6 months. The Sun's galactic velocity points towards Cygnus. Adding numbers that point in different directions by simply putting a plus sign between them is wrong, even in the cases where the chain is legitimate. Half the time the components partly cancel. At 2 points in every year, Earth's orbital velocity actually subtracts from the Sun's galactic velocity rather than adding to it. But the vector objection, although correct, is the smaller problem, and I do not want it to distract from the larger one. The larger one is that these numbers were never rungs on a single ladder in the first place. Think about what a ladder implies. It implies that as you climb, you get closer to something. It implies that the number at the bottom is a limited local truth, and the number at the top is the real answer, and that the ones in between are progressively better approximations. That is the emotional shape of the standard telling, and it is why the standard telling feels like it is going somewhere. You start with your chair and end with the universe, and it feels like a revelation. But physics does not agree that the top of that ladder is more true than the bottom. There is no sense, in any equation anyone has ever written down, in which your speed relative to the galactic center is a more genuine fact about you than your speed relative to your chair. They are both relationships. They are both measured. They are both exactly as real as each other. The only thing that makes one feel more impressive is that it is a bigger number, and a bigger number is not a truer one. So the chair is still standing there, at the bottom of a ladder that turns out not to be a ladder, and it has one property that none of the others have. It is the only second object in the entire list that you can reach out and touch. You can verify your speed relative to it with your own hand. Every other number in this video is a claim about your relationship to something you have never been near, which is where we would have to stop if the video were only about grammar. But it is not, and this is the point where the whole thing turns. So I want to state the new question as sharply as I can. If every speed is a relationship, and a relationship requires you to choose a second object, then the only way the word really can mean anything is if there is a second object whose choice is not arbitrary, not a bigger one, not a more distant one, a non-arbitrary one, something you did not simply pick. That is a much harder requirement than it sounds, and you can see immediately that nothing we have met so far satisfies it. Your chair is arbitrary, and you happen to sit in it. The Earth's axis is arbitrary. The sun is arbitrary. The local stars are a slightly less arbitrary choice, because they are an average rather than a single object. But the set you average over is one you drew a boundary around by hand. The galactic center is a real physical structure, but the galaxy is one of 2 trillion, and choosing ours is exactly the sort of parochialism physics has spent 400 years learning not to do. It is worth being precise about what is and is not being claimed here, because the objection I get at this point is a fair one. Somebody will say, fine, but if I want to know how fast I am moving relative to the center of the galaxy, I really can chain those velocities together properly using vectors and get an answer. And that is completely true. You can. Astronomers do it constantly. What you are doing when you do that is not climbing a ladder. You are performing a series of vector subtractions to convert a measurement made against one second object into a statement about a different second object. That is legitimate arithmetic, and it is how every number in the second half of this video was obtained. The mistake is not the chaining. The mistake is believing that the thing you arrive at is more real than the thing you started with, rather than just being about something further away. There is one more consequence of the relational picture that is worth stating now, because it will matter enormously at the end. All of this so far has assumed we can meaningfully compare the velocity of 2 objects that are in different places. In everyday physics, that assumption is harmless. In general relativity, it is not. Velocity is fundamentally a comparison between 2 things at the same location. To compare the motion of something here with the motion of something a billion light-years away, you have to carry one of those comparisons across curved space-time, and the answer you get depends on the route you carry it along. There is no unique answer. I am flagging it now and leaving it, because it is the 4th and final qualification on the number this video is building toward, and it is the one that does the most damage. And physics did try. For 2 centuries the ether was the candidate, and the ether would have qualified perfectly, because it was supposed to fill everything and be the medium light propagates in, and nobody would have picked it. It would have been given to us. And in 1887, the search for it returned nothing at all. So for a while, after 1905, the answer looked settled and slightly bleak. There is no absolute rest. There is no privileged frame. The question has no answer, only a list of relationships. And anyone who asks how fast we are really moving is making a grammatical mistake rather than a physical inquiry. That was the honest state of the subject for about half a century. And then, in 1964, 2 engineers at a laboratory in New Jersey found some noise in an antenna that they could not get rid of, and physics quietly acquired a second object it had not chosen. Before we can look at it, though, there is one more layer of the ladder to climb, and it is the largest coherent motion this planet takes part in. It is 631 kilometers per second, and roughly half of it is caused by something that is not there. Part 8. The half of it that is a push. The local group is the small collection of galaxies our own belongs to. There are perhaps 80 or so members, but almost all of the mass sits in two of them, the Milky Way and Andromeda, with the Triangulum galaxy a distant third, and everything else a scattering of dwarfs. The local group is moving, as a unit, at 631 kilometers per second, plus or minus about 20, and we will get to what that is measured against shortly, because that part is the hinge of this whole video. For now, take the number. It is the largest coherent motion that this planet takes part in. Everything we have discussed so far is a detail riding on top of it. 631 kilometers per second is about 2.3 million kilometers per hour. It is roughly 20 times the Earth's orbital speed and about 2.5 times the Sun's galactic orbital speed. It is 1/500th of the speed of light. And the question that occupied astronomers for most of 40 years was simple. What is doing this? Something has to be pulling. The first serious answer came in 1987 from a group of 7 astronomers whose names are worth saying because the collaboration acquired an unusually good nickname: Lyndon Bell, Faber, Burstein, Davies, Dressler, Terlevich, and Wegener. The 7 samurai. They measured the peculiar velocities of about 400 elliptical galaxies, which means they measured how fast each one was moving over and above the general expansion of the universe, and they found that the motions were not random. Galaxies across a huge region of sky were streaming coherently in the same direction, toward a point roughly in the direction of the constellation Centaurus. They called it the Great Attractor, and the name has stuck despite being slightly misleading. It is misleading partly because the Great Attractor sits in one of the most frustrating parts of the sky. From our position inside the Milky Way's disk, about 20% of the celestial sphere is blocked by our own galaxy's dust and stars. Astronomers call it the zone of avoidance, and the Great Attractor is in it. So for years we knew there was something there, because we could see everything around it moving toward it, and we could not look at it. Radio and infrared surveys, which see through dust far better than visible light, eventually filled in the picture. Near the center of it sits the Norma cluster, catalogued as Abell 3627, a rich cluster of galaxies about 220 million light-years away. But the Norma cluster is not massive enough to account for the whole flow. Behind it, roughly 4 times further out, at around 650 million light-years, lies the Shapley concentration, first noticed by Harlow Shapley in 1930, which is the largest concentration of mass anywhere in the nearby universe. It appears that the Great Attractor region and the Shapley concentration are, between them, doing much of the pulling. In 2014, Brent Tully and colleagues took the whole velocity field and used it to redraw the map in a genuinely new way. Instead of defining a supercluster by where the galaxies are, they defined it by where the galaxies are going. Take the flow lines, follow them, and see which ones converge on the same basin. On that definition, the Milky Way sits inside a structure about 520 million light-years across, containing something like the mass of 100,000 Milky Ways, whose flow lines all drain toward the Great Attractor region. They named it Laniakea, from Hawaiian words meaning immeasurable heaven. That is our address, if you want one. Earth, the Solar System, the Orion Arm, the Milky Way, the local group, the Virgo supercluster, Laniakea. And then, in 2017, Yehuda Hoffman, Daniel Pomerade, and Brent Tully published the piece that turns this from an interesting map into something genuinely unsettling. They mapped the flows in 3 dimensions and asked what combination of gravitational sources would produce the motion we actually see. And the answer that came out was that attraction alone does not do it. Roughly opposite the Shapley direction, on the other side of the sky, there is a large region where there is less than average. Not a void in the sense of absolutely nothing, but a substantial underdensity, sitting around 15,000 kilometers per second away in redshift units, which is on the order of 600 million light-years. And that region contributes roughly as much to our motion as the Shapley concentration does. They called it the dipole repeller. Now, an underdensity does not push. There is no repulsive gravity here, nothing exotic, no new physics. But gravity, in an expanding universe, only cares about differences from the average. If you are being pulled equally hard in every direction, you go nowhere. What moves you is the imbalance. And a region with less mass than average pulls you less than average, which means that relative to everything else, it is as though you were being pushed away from it. The mathematics is identical. The effect is identical. Nothing is there, and the nothing is steering you. I want to sit with that for a moment, because it is one of the 2 or 3 genuinely strange facts in this entire subject. You are moving at 631 kilometers per second. That is the single largest motion your body takes part in, and it contains every other number in this video inside it as a small correction. And approximately half of it is caused by an absence, not by an object, by a place on the far side of the observable sky where there is less than there should be. The intuitive picture of gravity is that things do it, masses pull. But in a universe that is expanding uniformly, being pulled by everything is the same as being pulled by nothing, and what actually moves you is the difference. In that world, an emptiness is as much of an agent as a mass, and the largest thing happening to you right now is roughly half agent and half absence. Before the coda, there is one piece of the local group's internal motion worth having, because it has just changed, and almost nobody has heard. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second along the line of sight. That is real motion, in the ordinary sense. The local group is gravitationally bound, so it has decoupled from the general expansion, and its members genuinely move toward and away from each other, the way objects in a room do. For decades, that approach was quoted as a certainty. In something like 4.5 billion years, the two galaxies would collide and merge. The merged object was even given a name, and the encounter appeared in every popular account of the future of the sky. Then, in 2025, a team led by Til Sawala published an analysis in Nature Astronomy that did something obvious in hindsight and difficult in practice. Instead of taking the best current values for every galaxy's position, velocity and mass, they took the full uncertainties on all of them and ran 50,000 Monte Carlo samples, propagating every error bar forward for 10 billion years. They also included the other massive members of the group properly, in particular the Large Magellanic Cloud, whose orbit runs close to perpendicular to the Milky Way and Andromeda line, and therefore tugs the whole encounter sideways. Across those 50,000 futures, the probability of a merger within the next 10 billion years came out close to 1/2, a coin flip. The collision was never a prediction of a dynamical law. It was a prediction that depended on a sideways velocity we have measured only barely well enough to have a sign for. Hold on to that too, because we are about to look at a number quoted to 5 significant figures, and the lesson of Andromeda is what a confident-sounding astronomical fact can look like from the inside. There is a coda to this that keeps the whole picture honest. In 2020, using the same catalogue of galaxy motions, the same group identified a structure they called the South Pole Wall, a filament roughly 1.4 billion light-years long, running across a large part of the southern sky. It had gone unnoticed until then, largely because much of it lies behind the plane of our own galaxy. A structure larger than the Great Attractor, in our own cosmic neighborhood, found in 2020. The map is not finished. Which brings us, at last, to the question I have been deferring since the beginning. 631 kilometers per second, relative to what? Part 9. The frame that nobody chose. In 1964, at Bell Telephone Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson had a problem with an antenna. The antenna was a horn reflector, a large aluminium funnel about 6 meters across, built originally to bounce signals off early communications satellites. Penzias and Wilson wanted to use it for radio astronomy, which meant they needed to understand every source of noise in the system down to a fraction of a degree, and there was a hiss they could not account for. It was not much, a background equivalent to about 3 degrees above absolute zero, but it would not go away. They checked everything. They ruled out the receiver. They ruled out New York City, 40 kilometers away, by pointing at it and seeing no increase. They ruled out the atmosphere by watching how the signal changed with angle above the horizon, and it did not change. They ruled out the residue of an atmospheric nuclear test some years earlier. They found a pair of pigeons nesting in the horn, evicted them, cleaned out what Penzias delicately called a white dielectric material, and the hiss remained exactly where it had been. It was the same in every direction, and it was the same at every hour of the day and every month of the year, which meant it was not coming from the sun, not from the galaxy, and not from anything on Earth. About 60 kilometers away, at Princeton, a group led by Robert Dick was building an instrument to look for precisely this. The theory said that the early universe was hot and dense, that for about 380,000 years it was an opaque plasma, and that when it cooled enough for electrons and nuclei to combine into neutral atoms, the light suddenly found itself able to travel freely. That light has been traveling ever since, stretched by the expansion of the universe into the microwave band. A phone call connected the two groups, and the two papers were published side by side. The cosmic microwave background is the oldest light there is. Its temperature today is 2.7255 Kelvin, and that figure comes from an instrument on the COBE satellite, whose measured spectrum remains the closest thing to a perfect blackbody ever found anywhere in nature. And it is almost, but not quite, the same in every direction. I want you to stand somewhere dark and imagine holding an instrument that does not read brightness but temperature, and sweeping it slowly across the whole sky. Everywhere you point it, it reads 2.7255. Turn toward the plane of the galaxy, and the galaxy itself glows in your instrument, but subtract that away, and the background beneath is still 2.7255. Turn to the empty places between everything, 2.7255. And then you notice something. It is not exactly constant. There is a very slight gradient across the whole sky, a broad warm half and a broad cool half, and the difference between the warmest point and the coolest is about 6.5 thousandths of a degree. 3.33 thousandths above the average on one side, 3.33 below on the other. The warm center lies in a small, dim constellation almost nobody can name. That gradient is the largest single feature in the entire microwave sky. It is roughly 100 times bigger than all of the primordial temperature fluctuations put together, the ones that eventually became galaxies, which are down at the level of a few tens of millionths of a degree. Now here is the turn. That warm spot is not a place. There is nothing there. It is not a hotter region of the early universe. It is not a structure, and if you flew toward it for 1 billion years, you would find nothing when you arrived. It is a direction. It is the direction you are going. This is the same effect Bradley found in starlight, and its close cousin. Move through a bath of radiation, and the radiation ahead of you is blue shifted, which for a thermal spectrum means it looks slightly hotter, and the radiation behind you is redshifted, which means it looks slightly cooler. The pattern that produces on the sky is exactly a dipole, one warm pole and one cool pole, varying smoothly between them. And because the physics of the Doppler shift is completely understood, the size of the temperature difference, divided by the average temperature, gives you your speed as a fraction of the speed of light, directly, with no model of anything else required. This was not a surprise when it was found. It was predicted. Peebles and Wilkinson wrote up the expected dipole in 1968, 4 years after the background itself was discovered, precisely because they realized that any observer moving through it would see one. The first credible detections came in the late 1970s from instruments flown on U-2 aircraft high above most of the atmosphere. COBE nailed down its form in the early 1990s, and the Planck satellite, which mapped the whole microwave sky between 2009 and 2013, gave us the number we use today. There are 2 more details about the dipole that are worth having, and both of them are quietly astonishing. The first is that our motion does not only change the temperature of the microwave sky, it also moves things on it. The same aberration effect that displaced Bradley's stars by 20.5 arcseconds applies here too. So the small hot and cold spots in the background are very slightly crowded together in the direction we are heading and very slightly spread out behind us. Planck detected that crowding. It is a completely independent fingerprint of the same motion, and it is going to matter enormously in about 15 minutes. The second is a small piece of bookkeeping that tells you how seriously this is taken. The dipole is removed, by default, from every published map of the microwave background. Every image you have ever seen of the infant universe, the mottled ovals in blue and red, has had our own motion deliberately subtracted out of it first, because otherwise the entire picture would be swamped by a warm half and a cool half 100 times larger than the pattern anybody wants to look at. Our velocity is not a signal in those maps. It is a contaminant, and it is the first thing thrown away. There is even a case where the traffic runs the other way. The Earth's own orbital motion, 30 kilometers a second, imprints a small annual wobble on the measured dipole. Because we know Earth's orbital speed to far better precision than we need, that wobble is used as a calibration standard. The instrument is checked against our motion, rather than the other way round. But before I give you the number, I have to explain why this frame is different from every other second object in this video, because if I do not, you will draw the wrong conclusion from it, and it is the wrong conclusion almost everybody draws. The cosmic microwave background does not restore absolute space. It does not mean Einstein was wrong. It does not resurrect the ether. And the reason is a distinction that takes about 2 minutes to state and is worth every second. Relativity's claim is about the laws of physics. It says that the laws are identical in every frame, moving at constant velocity. No experiment on the laws, no measurement of the speed of light, no particle collision, no comparison of clocks can distinguish one such frame from another. That claim is exactly as intact today as it was in 1905. The microwave background is not an exception to it, and nothing about it lets you detect your motion by any experiment performed inside a sealed room. If you shut the door, you are back in Galileo's cabin, and you are stuck there. What the microwave background gives you is not a preferred frame of the laws. It is a preferred frame of the contents. The universe happens to contain a nearly uniform bath of ancient light, left over from its own origin, spread across everything. That bath happens to define, at every point, one particular state of motion, in which it looks the same in all directions. That is a fact about what is in the universe, not a fact about the rules the universe runs on. And the distinction is not a dodge, it is the whole of the answer. Think of a large room full of perfectly still air. The laws of physics do not prefer the frame of the air. A person running through the room is not doing anything illegal, and every experiment they perform on the laws will give the same answers as the person standing still. But still relative to the air is nevertheless a meaningful, non-arbitrary description, and it is the one that determines whether your hair is blowing about. Nobody chose the air. It was already there. The cosmic microwave background is the universe's still air, and the crucial thing about it, the thing that finally satisfies the requirement we set in Part 7, is that we did not pick it. It is not our galaxy, or our neighborhood, or a boundary we drew around a set of stars we happened to be able to see. It is the light of everything, from before there was anything to see, arriving from every direction at once. So we have found our second object. It is not privileged by physics, it is privileged by the fact that it is everything else, which means we can finally state the number. Part 10, 369.82. The Planck satellite's final data release gives the velocity of the solar system with respect to the cosmic microwave background as 369.82 kilometers per second, plus or minus 0.11. The direction is galactic longitude 264.021 degrees, galactic latitude 48.253 degrees. Translated onto the ordinary sky, that is a point inside the constellation Crater, the Cup, a small and faint pattern of stars just below Leo, containing nothing anybody has ever had a reason to look at. If you can find the sickle of Leo on a spring evening and drop your eye down and to the south, you are looking roughly at the direction the solar system is traveling with respect to the oldest light in the universe. Take a moment with the size of the number first. 369.82 kilometers per second is about 1,331,000 kilometers per hour. It is more than 12 times the Earth's orbital speed. It is about 1/800th of the speed of light, which means that if you could look at the whole solar system from outside, from a position at rest in that ancient light, the entire arrangement, the sun, the planets, the comets, all of it, would be crossing a distance equal to the Earth-Moon separation about every 17 minutes. It also comfortably beats anything humanity has ever built. The fastest object ever made by human beings is the Parker Solar Probe, which at its closest approaches to the Sun, reaches something in the region of 690,000 kilometers per hour. That is a machine designed specifically to go fast, dropped down the Sun's gravitational well to do it, and it is not quite half of the speed you are getting for nothing while sitting still. Voyager 1, which has been traveling outward for nearly 50 years and is the most distant human object, is doing about 17 kilometers per second. You are doing more than 20 times that, right now, without having done anything. But it is not the size of the number that I want you to notice. It is the number of digits. 369.82 plus or minus 0.11. That is 5 significant figures, and an uncertainty of about 3 parts in 10,000. And the direction is quoted to 1,000th of a degree, with an error ellipse a few arcseconds across. To get a feel for how small that is, consider that the full moon is about 1,800 arcseconds across. If you held the entire uncertainty in the direction of your motion through the universe at arm's length, it would be far too small to see. Astronomers have located the direction we are heading to within a region of sky hundreds of times smaller than the moon. Stop and compare that to anything else you know about your own motion. The speedometer in a car is accurate to a few percent. On a good day, your speed relative to your chair is 0, which is precise but not informative. Nothing you have ever been told about how fast you are going is known to 5 figures. This one is. And by the standards of this video, it also passes the test we set. It is measured against something we did not choose, that fills everything, that is not ours, that predates every structure in the universe. It is the closest thing to a non-arbitrary second object that anybody has ever found. There is one more thing about the number worth saying before we take it apart, and it is a piece of perspective rather than a caveat. 369.82 kilometers per second is, cosmically speaking, boring. Galaxies typically move relative to their own local patch of the microwave background at a few hundred kilometers per second, which is what you would expect from the gravitational tugging of large-scale structure. We are not fast. We are not slow. We are a very ordinary galaxy group, drifting at a very ordinary rate through a universe full of galaxy groups doing the same thing. That ordinariness is itself a data point, and a reassuring one. If our velocity had come out at 5 kilometers per second, or at 50,000, cosmologists would have had a serious problem, because the theory of how structure grows predicts the distribution of these peculiar velocities fairly tightly. We came out squarely in the middle of the predicted range. The model that says a nearly uniform early universe gradually clumped under gravity into the pattern we see today also says that a galaxy in that pattern should be doing a few hundred kilometers a second relative to the ancient light, and we are. It is also worth being clear that there is no single global version of this frame. Every galaxy in the universe has its own local microwave rest frame, defined by where its own dipole vanishes. And they do not agree with each other, because the universe is expanding, and the light arriving at each place has come from a different distance in a different direction. There is no cosmic speedometer bolted to the outside of everything. There is a local definition of still, available at every point, and ours is the only one we will ever be inside of. So I could end here. A great many treatments of this subject do. 369.82 kilometers per second, toward crater. Roll credits. I am not going to, and here is why. I have given you a number and a very small uncertainty attached to it, and I have not yet told you what that uncertainty is a statement about. Those are not the same question, and the gap between them is where the rest of this video lives. There is a rule of thumb worth carrying around in any science, and it is this. When a quantity is quoted to a precision that seems out of proportion to the difficulty of measuring it, the extra digits are usually not measuring the thing you think they are measuring. They are measuring something adjacent, which has then been converted into the thing you asked about by a step that involves an assumption. The digits belong to the easy part. The assumption is the hard part, and it does not carry an error bar. We saw a small version of this earlier tonight, with the distance to the galactic center. Two teams, using the same technique and the same star, quoted precisions of 3 and 4 parts in 1,000, and their answers differed by more than 1%. Neither had done anything wrong. There was simply more slop in the world than either analysis knew how to account for. The 369.82 figure has an assumption in it. It is a good assumption. It is almost certainly close to true. Until quite recently, nobody had ever tested it independently, because nobody knew how. Somebody worked out how. And when they did it, the answer they got was 300 plus 111 minus 93. Both of those are measurements of the same velocity. Let me show you why they are so different, and what that difference actually tells us. Part 11. What the plus or minus is actually measuring. The assumption inside 369.82 has a name. It is called the kinematic assumption, and it says that the entire dipole in the microwave sky is caused by our motion, and that none of it is intrinsic to the universe itself. To see why that is an assumption, rather than an observation, think about what the measurement actually consists of. Planck maps the temperature of the sky. It finds a pattern that is warm on one side and cool on the other, with a peak-to-trough difference of about 6.5 thousandths of a degree. That is what is measured. To turn it into a velocity, you divide the amplitude of that gradient by the average temperature and multiply by the speed of light. The arithmetic is trivial, and the physics is beyond dispute. But notice what that calculation quietly requires. It requires that all of the warm-cool gradient came from the Doppler shift of our motion, and that the early universe itself was not, in some small way, already slightly warmer on one side than the other before we ever started moving through it. Why would the early universe be lopsided like that? It probably is not, and there is a decent theoretical reason to expect it is not. Inflation, the proposed period of enormous expansion in the first fraction of a second, takes a tiny patch of space and stretches it to beyond the size of the observable universe, which is exactly why the background is so uniform in the first place. A patch that's small, and that causally connected, has no way to acquire a large-scale lopsidedness. But probably not is not the same as measured to be not. And there was, for a long time, no way to check. The dipole is one number, and if you only have one number, you cannot separate two contributions to it. The check exists because motion leaves more than one fingerprint on the microwave sky. I mentioned the second fingerprint at the end of part 9. Motion does not only shift temperatures, it aberrates positions. Every hot and cold spot in the pattern gets nudged slightly toward the direction of travel, in exactly the manner Bradley found for stars in 1728. And there is a third fingerprint too. Motion modulates the amplitude of the small-scale fluctuations, making them look very slightly larger in angular scale ahead of us, and smaller behind. Here is the crucial point about those two extra fingerprints. They depend on our velocity, and they have nothing whatsoever to do with the dipole's amplitude. They are not derived from it. They show up in a completely different part of the data, in the correlations between fluctuations at different angular scales, and they can be extracted independently. So in principle you can do this. Ignore the dipole entirely. Do not use it. Measure the velocity from the aberration and modulation signals alone, which cannot be faked by any intrinsic lopsidedness of the early universe. Then compare the answer to what the dipole says, and the difference between them is a direct measurement of how much of the dipole is not ours. In 2021, Pedro da Silveira Ferreira and Miguel Quartin published exactly that analysis in Physical Review Letters, using the Planck data. It was the first time anyone had measured our velocity without assuming the answer. The result was 300 kilometers per second, plus 111, minus 93. And their upper limit on any intrinsic component of the dipole was 3.7 thousandths of a degree, at 95% confidence. Now read those two numbers together, carefully, because it is easy to take the wrong thing from them. The first thing to say is that the two measurements agree. 300, with an uncertainty of around 100 either way, comfortably contains 369.82. Nothing has been contradicted. Nobody has shown that the kinematic assumption is wrong. If you had to bet, the standard picture is still overwhelmingly the way to bet. The second thing to say is the one that matters for this video. Look at the error bars. The dipole-based figure has an uncertainty of 0.11 kilometers per second. The independent figure has an uncertainty of around 100. That is a factor of roughly 1,000. So here is what the 5 significant figures in 369.82 are actually the precision of. They are the precision with which the amplitude of a temperature gradient across the sky has been measured. That measurement is superb, and it deserves every one of those digits. What it is not is the precision with which our velocity is known, because between the gradient and the velocity there is a conversion step that rests on an assumption, and the only direct test of that assumption can currently confirm it to about 30%. The precision of the measurement and the precision of the knowledge are two different numbers. In this case, they differ by a factor of 1,000. It is worth pausing on how difficult the Ferreira and Quartin measurement is, because the size of the error bar is not a criticism of the work. The dipole is 6.5 thousandths of a degree, which sounds tiny until you compare it with what they were working with. The aberration signal is a shift in the positions of features on the sky by an angle of roughly 4 arc minutes, spread across a pattern of hot and cold spots that are themselves about a degree across and irregular, with no sharp edges to measure against. There is no single spot you can point at and say, that one has moved. The signal only exists statistically, as a correlation between the fluctuation pattern at one angular scale and the pattern at a neighboring scale, and you have to dig it out of a map that also contains the galaxy, foreground dust, instrumental noise, and the primordial pattern you are trying to measure the shift of. Getting any velocity at all out of that is an achievement. Getting one accurate to 30% is remarkable. And the fact that the best independent check available to us is accurate to 30%, while the headline figure carries 5 significant figures, is not a failure of the check. It is a fact about which parts of the problem are easy and which are hard. There is a companion question hiding in the same analysis, and it is the one cosmologists actually care about. An intrinsic dipole would not be a measurement problem. It would be a physical statement about the early universe having a preferred direction. The ceiling of 3.7 thousandths of a degree does not rule that out. It bounds it. Somewhere under that ceiling, there is room for a small, real, primordial lopsidedness, and nobody currently knows whether the room is occupied. None of that makes the headline figure wrong. I want to be careful, because the failure mode in popular science is to take an honest caveat and turn it into a scandal. 369.82 kilometers per second is very probably correct to within a few kilometers per second, and it is used, correctly, throughout professional cosmology. What has happened is narrower and more interesting than a scandal. A number that everybody quoted, as though it were a raw measurement, turns out to be a raw measurement plus an inference. And somebody finally worked out how to test the inference, and the test came back consistent but blurry. That is the first crack, and on its own it is a footnote. The second crack is not a footnote, because there is another way to measure our motion, one that has nothing to do with the microwave background at all, and it does not agree. Part 12. A million quasars disagree. The second method is beautifully simple, and it was proposed in 1984 by George Ellis and John Baldwin, long before anybody had the data to use it. Start with the assumption that underwrites essentially the whole of modern cosmology, the cosmological principle. It says that on large enough scales the universe is statistically the same everywhere and in every direction, not identical, but the same on average. No preferred place. No preferred direction. If that is true, then an observer genuinely at rest with respect to the large-scale universe should count the same number of distant objects in every direction. Take a survey of very distant galaxies or quasars. Split the sky in half any way you like, count, and the two halves should match within the ordinary statistics of counting. A moving observer should see something different, for 2 reasons that both point the same way. Aberration crowds the sources slightly toward the direction of travel, exactly as it crowded Bradley's stars and the microwave background's hotspots. And Doppler boosting makes the sources ahead of you slightly brighter, which pushes a few of the faintest ones over the survey's detection threshold, so a handful of objects that would otherwise be invisible get counted. Both effects add a slight excess of sources in the direction you are moving. Ellis and Baldwin worked out how big the excess should be, and it depends on the survey's own properties, chiefly how steeply the number of sources rises as you look at fainter ones, and on the colors of the objects. For a typical quasar survey, the predicted excess is about 0.5%. I want you to hold the shape of this experiment in your head, because it is one of the most elegant measurements in cosmology and one of the least known. Imagine dividing the entire sky into 2 hemispheres, one centered on the direction the microwave background says you are moving, and one centered on the opposite point. Now count every quasar in each half. Not a sample. All of them, more than 1 million objects, catalogued by an infrared survey that spent years mapping the whole sky. 2 enormous numbers, differing by a fraction of a percent. That fraction, and the direction that maximizes it, is your velocity through the universe, measured with nothing but arithmetic and a very long list. And if the standard picture is right, that measurement must agree with the microwave background. It has to. Both are supposed to be tracing the same large-scale universe. In 2021, Nathan Seacrest and colleagues did it, using about 1.36 million quasars, selected from a wide-field infrared survey catalogue, chosen carefully to be genuinely distant and to avoid contamination from anything nearby. They found a dipole. It was in the wrong place, and it was too big. The direction came out at galactic longitude 238.2 degrees, latitude 28.8, which is 27.8 degrees away from the direction the microwave background gives. And the amplitude came out at roughly twice what the kinematic prediction says it should be. The statistical significance of the discrepancy was 4.9 sigma. The following year, a joint analysis combining a large radio galaxy survey with the same infrared quasars raised it to 5.1 sigma. A separate Bayesian reanalysis by another group found the amplitude 2.7 times the expected value, at 5.7 sigma. Independent work using a different quasar catalogue has found consistent excesses. 5 sigma is the threshold that particle physics uses to declare a discovery. It is roughly a 1 in 3.5 million chance of arising from statistical fluctuation alone. This result has now been reproduced with different catalogues, at different wavelengths, by different groups, using different statistical machinery. Nobody has found an accepted explanation. The candidate explanations exist, and they are being worked on seriously, because a systematic error is by far the most likely answer. Clustering that has not been fully accounted for. Evolution in the population of quasars with distance. Contamination from nearby structure. Calibration gradients across a survey that was assembled from many separate scans of the sky. Each of these reduces the significance in some analyses. None of them so far eliminates it. It is worth being concrete about how small the effect under dispute is, because that is what makes it so hard to settle. The predicted excess is about half of 1%. The measured excess is around 1%. In a catalogue of 1.36 million quasars, the difference between those two predictions is roughly 5,000 objects. 5,000 faint infrared points of light, out of 1.3 million, distributed across the whole sky, is the entire evidence base for the strongest current observational challenge to the assumption that the universe looks the same in every direction. Every one of those objects had to be identified, its distance category assigned, its colors checked, and anything nearby or misclassified thrown out, across a survey stitched together from years of scans. That is why the systematic explanations are taken so seriously, and it is also why they have been so hard to make stick. A 1% gradient in how efficiently a survey detects faint objects across the sky would produce exactly this signal, and surveys do have gradients like that. But the gradients that have been looked for are not in the right direction and not of the right size, and when different surveys at completely different wavelengths, built by different teams with different instruments and different failure modes, produce the same excess, pointing the same way, coincidence starts to become expensive. The test also has 2 soft spots that its critics correctly keep pointing at, and it is only fair to name them. The predicted amplitude depends on 2 survey-specific quantities: how steeply the number of sources climbs as you go fainter, and the average spectral color of the population. Get either wrong, and your prediction moves. Both have been examined repeatedly, with the numbers measured directly from the same catalogues, rather than assumed, and the excess survives any reasonable variation in either. It shrinks a little under some choices, and it grows under others, and across the full range of defensible assumptions, it stays above the threshold that would normally be treated as a detection. That is the state of it as of tonight, which leaves two possibilities. The first is that a subtle systematic is hiding somewhere in a survey of over 1 million objects and will eventually be found, and the anomaly will dissolve the way most anomalies do. This is very probably what will happen. It usually is. The second is that the cosmological principle is not exactly right. That the universe, on the largest scales we can see, is not quite the same in every direction. If that is the case, then the assumption that the microwave background defines the frame of everything else has a hole in it, because everything else does not agree with the microwave background about which way we are going. I want to be careful about the weight I put on this. The standard picture is not in danger tonight. Most anomalies of this kind resolve into instrumentation, but it is worth registering that this is not the only large-scale tension currently on the books. The expansion rate of the universe inferred from the microwave background, 67.4 kilometers per second per megaparsec, disagrees with the value measured directly from nearby distance indicators, 73.04, at more than 5 sigma, and that disagreement has resisted resolution for over a decade, despite enormous effort. 2 independent 5 sigma disagreements about the large-scale universe is not a comfortable place for a model to sit. There is also an older and messier claim in this territory worth mentioning honestly. In 2008, a group led by Alexander Kashlinsky reported that clusters of galaxies were streaming coherently at several hundred kilometers per second out to distances far beyond where the standard model says such flows should die away. It was named dark flow, and it generated a substantial popular literature suggesting that something outside the observable universe was pulling on us. The Planck collaboration analyzed the same effect in 2014 and found no significant signal. The claim has not been confirmed. It has also not entirely gone away, and it should be reported as a live question rather than as an answer, and certainly not as evidence for another universe, which is the least testable of all the available explanations. So here is where we have arrived, with one part left. We have a number, quoted to 5 significant figures. We have a direct test of the assumption behind it that can only confirm it to about 30%. And we have an independent method using 1 million distant objects that says we are going a different way, twice as fast, at a significance that in any other branch of physics would be a headline. It is time to answer the question. Part 13. How fast we really are moving. Here is the answer. You are moving at 369.82 kilometers per second toward a point in the constellation Crater, below the sickle of Leo, and you have been doing it your whole life. That is about 1,331,000 kilometers per hour. It is more than 20 times the speed of the most distant object humanity has ever launched, and it is faster than anything anyone has ever built, and you are getting it for nothing. That number earns the word really, and I want to be precise about why, because the reason is not the one most people would give. It does not earn it by being the biggest. It is not the biggest. It does not earn it by being the most fundamental, because there is no such thing as a more fundamental velocity. It earns it because of what it is measured against. Every other number in this video required you to choose a second object: your chair, the rotation axis, the sun, the nearby stars, the center of one galaxy out of 2 trillion. Each of those choices was made by a human being, for human reasons, and physics is indifferent to all of them. The oldest light in the universe is the 1-second object nobody picked. It is not ours. It fills everything. It arrived from every direction at once, from before there was anything at all to look at, and it happens to define, at every point in space, one particular state of motion in which it looks the same in all directions. That is the whole of what really turns out to mean, not a privileged frame of the laws of physics, which does not exist, and which Michelson and Morley proved does not exist in a basement in Ohio in 1887, a privileged frame of the contents. The universe is still air, and the number that comes out of it rests, in the end, on the fact that one broad half of the sky is about 0.003 of a degree warmer than the other. So that is the answer, and it arrives carrying 4 qualifications, and I would not be doing this properly if I gave you the first without the rest. The first qualification is that it does not restore absolute space. Nothing, in the last 2 hours, has undone Galileo's cabin. If you seal the door and run every experiment you can devise on the laws of physics, you will find nothing that tells you your velocity. The microwave background is detectable only because it is stuff out there that you can look at. Take it away, and the word really loses its referent again immediately. The second qualification is the one about the digits. 369.82 plus or minus 0.11 is the precision of a temperature measurement converted into a velocity by a step that assumes the entire gradient is ours. The only independent test of that assumption returns 300 kilometers per second plus 111 minus 93. The two agree, but the precision of the measurement and the precision of the knowledge are different numbers, and in this case they differ by a factor of about 1,000. The third qualification is that the distant universe currently disagrees. Count more than 1 million quasars across the sky, and the direction they say we are moving is about 28 degrees away from the direction the microwave background gives, with an amplitude roughly twice as large, at a significance above 5 sigma, reproduced by several groups at different wavelengths. It is most likely a systematic that will eventually be found, but until it is found, the claim that the microwave background speaks for everything else has a hole in it, because everything else is not agreeing. And the fourth qualification is the largest, and it is the one that takes the question apart rather than the answer. There is no global answer at all, because in general relativity, moving through space is not a well-formed idea. Velocity is a comparison between two things at the same place. To compare your motion with the motion of something 1 billion light-years away, you have to carry that comparison across curved space-time, and the result depends on the route you take. Different routes give different answers, and none is correct. This is not a subtlety about instruments. It is why distant galaxies can recede faster than light without violating anything, and it is why their recession is not motion in the ordinary sense at all. There is no speedometer bolted to the outside of the universe, and there is no number for how fast we are moving through space, because space is not the sort of thing you move through. There is only how fast we are moving relative to a named thing at a named place. There is one more answer that people sometimes offer at this point, and it is a real and beautiful piece of physics, but it is the answer to a slightly different question, so I want to name it and set it down, rather than let it be mistaken for the payoff. In the geometry of space-time, every object can be said to move through space-time, rather than through space, at a fixed rate, and that rate is the speed of light, for everything, always. Sitting still means spending all of it moving through time. Moving quickly means trading some of that for motion through space, and aging more slowly by exactly the amount you traded. It is elegant, it is correct, and it answers the question, how fast are we moving through space-time? Our question tonight was through space, and through space, the answer stays relational, all the way down. I also want to say something about the shape of what happened here, because I think it is the real lesson, and it is not really about velocity at all. We started with a question that sounded like it was asking for a quantity, It turned out to be asking for a relationship. When we went looking for a relationship that was not arbitrary, we found one, and it was better than anyone in the 19th century had any right to expect, and it gave us 5 significant figures. And then, when we asked what those 5 figures were the precision of, the answer came apart in the hand slightly, not into nonsense but into something more textured, a superb measurement of one thing, converted into a statement about another thing by a step that is probably fine. That pattern is not a failure of this particular subject. It is what most well-understood things look like when you press on them hard enough. The confident number on the outside is usually a very good measurement of something adjacent, plus a bridge. The bridges are where the interesting arguments live, and they almost never appear in the summary, because a bridge is harder to put on a diagram than a number is. Which brings me back to where we started. You are sitting in a chair, and your speed relative to it is 0, and that has been true for the entire 2 hours we have spent together. I said at the beginning that it was a complete and correct physical statement, and not a lesser truth, and I want to close by telling you why I think it is worth more than it looked like at the start. The chair is the only second object in this entire video that you can reach out and touch. Every other number tonight was a claim about your relationship to something you have never been within 100 million kilometers of, measured by instruments you will never see, at the end of a chain of inference that we spent an hour taking apart. 369.82 kilometers per second is the better traveled number. 0 is the one you can check. And they are the same kind of statement. That is the thing I would like you to take away from tonight, rather than the number. Not that your stillness is an illusion, because it is not. Not that the truth was hiding at the top of a ladder, because there was no ladder. Just that every speed anybody has ever quoted you, for yourself or anything else, was secretly a sentence about 2 things, and the second thing was usually left out. Ask how fast we are really moving through space, and physics will hand you the number, 369.82 kilometers per second, toward a faint cup of stars below Leo, and then it will very quietly hand you the receipt. And the receipt says that the number is a relationship, that its last 3 digits belong to an assumption, that 1,000,000 quasars have filed an objection, and that the word through in the question was never quite right in the first place. The universe does have a still. It is made of light that has been traveling for 13.8 billion years. It is 0.003 of a degree lopsided, and we are falling across it at 1,000,000,000 kilometers an hour, toward a constellation that has no bright stars and no stories attached to it, for reasons that are about half a distant wait and about half an absence. And nobody yet knows whether the frame we measured it against is the one the universe actually has.